All right, so let's get started here. So this new unit, like I said, is kind of a combo unit. It's not going to be longer than other units because it's combining chapter 5 and 7, but not all the sections. We're actually only going to do 2 sections from chapter 5 and then probably 3 sections from chapter 7. So it'll be kind of a normal one. So chapter 5 is trig graphs is what we're going to look at. So we're going to take sine, cosine, and tangent, and we're going to graph them as a function, okay? And then we'll go into chapter 7 later on, and that's analytic trigonometry. So we'll really analyze the trigonometry, all right? Okay, so we're going to start off today graphing sine, cosine. Next week, we'll graph tangent. I'll tell you right now, you can also graph secant, cosecant, and cotangent. We're not going to do that because we don't have enough time this year, but it is possible, okay? Sine and cosine graphs are very much related to each other. We're going to see they're very, very similar to each other. Tangent is a little bit different than sine and cosine, but does have some similarities as well. So that's going to be interesting. We'll view all of that. Okay. Cool. So this is just kind of like its own family of functions, kind of like how we had like quadratic functions, right? You know about those. They're like the parabolas. Absolute value functions, that's like the V-shaped graph. We talked about all different types, right? Like what are some other ones? We did like talked about a square root function, a cubic function. So now these are like other types of functions, graphs, sine, cosine, and tangent. All right. Okay, got a lot of vocab here today. So the first couple pieces here is called periodic functions and then the period of a function. So those are very much related. So a periodic function is a function that repeats itself in a regular fashion, all right? And for sine and cosine, and I'm on the period of a function now, sine and cosine parent functions repeat every 2 pi, which means they have a period of 2 pi. So I'm going to kind of show you what that means here on the Desmos. So let's take a look at that. So I've put here sine x, all right? And so what's kind of unique about these trig graphs is that they have this, they are periodic, okay? So they have this cycle that repeats over and over and over again really forever. That's different than like, for example, a quadratic function, which is just one parabola wherever it is, and that's it, right? So this one, the period, like they said, was 2 pi. So if I go from 0 to 2 pi here, we see we have a hill, and then we have a valley, and then it kind of ends up there. And then it kind of does that over again, right? Another hill and then another valley, and then another hill and then another valley. And if you have time this weekend, you could actually keep scrolling this to the right forever, and it would never stop doing those hills and valleys, okay? And you can actually click on the different spots and kind of see what the high points, the low points, and the midpoints are as you go along. Not only does it go to the right forever, it actually also goes to the left forever, as you can see on the negative side. So kind of just repeating this, these little waves, okay? These hills and valleys, as I call them. So when we use that word period, I think about the periods in the class or my class periods throughout the day. All right. And so this really works well for me for an analogy. It doesn't work as well for you guys because your first period is kind of different than your second period, right? You learn different things. It's a different subject even, but for me, I kind of teach the same thing all day. All right. So let me tell you how my day goes and kind of link it up to the period on the sine graph. So let's say first period starts right here. So first period starts, all right. I welcome everybody into class. We do some notes. I show my techniques for doing certain problems. I tell some jokes. Then I show a meme, and then I kind of tell everybody to do WebAssign and then have a nice day, all right? And then first period ends. And you know what happens after that? Second period starts. And you want to know what I do during second period? I welcome everybody into class. I do the same exact notes using the same exact techniques. I tell the same exact jokes. I share the same exact meme. I tell people to do WebAssign. And then second period is over. And you want to know what happens after second period? Third period starts. And you know what I do during third period? I welcome everybody into class. I do the same exact notes.
The same routines.
Same exact techniques. I tell the same exact jokes. I share the same exact meme. And then I tell everybody to do WebAssign, and then I tell them to have a nice day. And this pattern will just complete itself over and over and over again for the rest of my career until I either retire or die, whichever comes first. Okay. So that's my life. And I actually love it. And some of you are looking at me like I'm crazy, but no, actually, I enjoy it. Okay. And people are like, oh yeah, how can you tell the same jokes over and over again? But like, you guys know stand-up comedians, they actually have what they call their set. Like they have their jokes and then they'll do like 2 shows a night and then like 3 shows over a weekend. And they're doing the same thing. They're telling the same jokes over and over. And you know what happens? You get good at telling those jokes, right? And so I get good at telling jokes. I get good at like teaching the material. I feel like I get better throughout the day. And so most of the time, like my second to last or my last class is probably my best. I'll call it a performance because I kind of think it is a performance, my best performance of the day. So I actually think it's an opportunity to redo what you've done throughout the day and do it better. So I actually think that's kind of cool. But maybe I'm a weirdo. Or that's not a maybe. I take that back. I'm a weirdo. So you might disagree with me. Okay, cool. So that's my kind of analogy there to understand the periods of the sine graph. Let's go back to the notes.
Goodness gracious.
All right. So here we have a sine graph, and I wanted to kind of introduce to you guys where we have one period of a sine graph here. And I've put the unit circle next to this so we can kind of see where the graph is coming from. And so I'm going to show you guys. So when we do the unit circle, we always start right here, correct? On the far right of the unit circle. And that, when we're talking radians here, because we're going to be talking radians the whole time. So if we're thinking about the unit circle, if I want the sine of 0 radians, that actually equals 0, okay? Because the coordinate point there is 1, 0, but we know that sine is the y value, correct? So sine of 0 equals 0, which means we start off at this point, 0, 0. Then if we went up here to this point is pi over 2. So if I was looking for the sine of pi over 2, if you remember on your unit circle, that's actually 1. And so that's why this point up here is pi over 2, 1. Then if I went over here to the left side of the unit circle, the radian value there is pi. And sine of pi is actually back to 0. So that's why this point is pi, 0. And if I went to the bottom of the circle, bottom of the unit circle, the radian value there is 3 pi over 2. And the y value of the point is -1. So that's why this point is 3 pi over 2, -1. And then 2 pi is actually in the same spot as 0 because 2 pi is like we went all the way around the circle and we're back to where we started. So of course that's still 0. So we have 2 pi, 0 to finish out the period. And then if I kept going, I would just kind of go around the circle with the coterminal angles in that same pattern, right? I'm going to go to the top, but it's going to be 1, and then it'll be back to 0, and it'll be back to -1, and then it'll be back to 0, just going around and around and around. Could I find some other values in between here, like pi over 3, pi over 4, pi over 6? Yeah, I could, but those are actually tough to graph because it's like, those are like the rad 2 over 2s and the rad 3 over 2s. They're tough to graph, so I usually just skip over those. So that's really where that kind of first period of the sine graph is coming from. All right, well, let's do it again here, but now let's do that for cosine, okay? So if we're going around the unit circle in kind of that same pattern for cosine, what's that going to look like? It's going to look similar, but a key difference. Actually, I'm going to start up here. All right, so if I have cosine of 0 radians, so if I'm starting off here, remember cosine is the x value on the unit circle, so that's actually going to equal 1. So my first point then will not be 0, 0, it's going to be 0, 1. Because at the radian measurement of 0, our cosine is 1. Then when I go to pi over 2, the cosine of pi over 2 is actually 0. So let me try to match this up here. There we go. So I got pi over 2 comma 0. All right, then when I go over to pi radians, halfway around the circle, cosine of pi is -1. So I have a point here that I'm going to call pi comma -1. When I go to the bottom of the unit circle, cosine of 3 pi over 2, that is actually back to 0. And then when I finish at 2 pi, I'm back to a cosine value of 1. So I'm right there. So notice on both of these, the last point in the period is always kind of at the same spot as the first point in the period, right? Because the period ends at kind of the same point that it starts. I kind of think of this, using my analogy again with the class periods, as the bell, right? The class period starts with a bell and it ends with a bell. And those bells really sound the same, right? Okay, so then this one is going to look like this. Now I told you that the sine graph was the period was one hill and one valley, correct? Now is the cosine graph also one hill and one valley? I'm actually going to argue yes, that the cosine graph is also one hill and one valley. Well, can we see the hill right, or sorry, can we see the valley right here in the middle? I think that's pretty easy to see, correct? In the middle, we have a valley. So that matches up with the valley that's over here. But where's the hill? Well, I'm going to say that the hill is kind of cut in half. So here over here on the far right is half of the hill. And then here on the far left is the other half of the hill. And if you put those two halves together, you would have a whole hill. So it's just kind of split up here, okay? And if we actually looked at the graph on Desmos, which I'd like to
If you go farther to the left or right, you would see a full hill.
You got it, Nicholas. You are absolutely correct here, because yes, we're kind of seeing the half of the hill on the one we drew, but if we went to the left, we would see the other half. And then this half of the hill that we did see on our graph, the other half is completed over there. So I agree wholeheartedly with your analysis there, Nicholas. Okay. Okay, so if we kind of look at these two graphs together, which I'll put them back up, you can actually see that they really are very similar, correct? They have actually the same exact shape. And actually, if you just move the red graph a little bit to the left, or you move the purple graph a little bit to the right, they would actually be the same exact graph. So that's why I'm saying these two very much connected, because they're literally the same graph, just kind of shifted left or right. All right. Awesome. So then what's the difference? Well, let's go back, compare and contrast here. And the big difference that I want to indicate up here, that's going to be kind of I'm going to keep repeating throughout this section, is that sine starts at a midpoint. Okay, so I kind of see all these points as high points, midpoints, or low points. Sine will always start at a midpoint. Okay, we can see our sine graph here starts at a midpoint and goes up from there. We are going to see some sine graphs that start at a midpoint and then go down from there. But either way, it's going to start at a midpoint. Okay. Cosine, what type of point does it start at? Well, according to our graph, it looks like it starts at a high point, correct? Now for that one, I'm actually going to say that one's usually true. I'd say about 80% of the time, 80% of the cosine graphs I see start at their high point. So what makes a cosine graph not start at its high point? We're going to see that today. We're going to see some of those 20% of cosine graphs that start at their low point. So hold that thought. We will get to it today, okay? But let's say for now, until otherwise instructed, cosine graphs start at their high point, okay? All right. All right, we got some more vocab coming up here. Oh, but first, I got a little typo here. If you guys could just change this one because these apply to both sine x and cosine x. Sine x, by the way, my favorite brand of nasal decongestant. Sine x. That was a joke that I've told for 4 times today. All right. No, but these apply to sine x and cosine x. All right. I think I did you guys ever do where you like do a copy paste and you're like, okay, I'm gonna go back and change that later and then forget to change it, your paste, your copy paste. That's I think what happened here. All right. So what's our vocab? Amplitude. Okay, so for these graphs, the amplitude is 1. Now they say here amplitude is the height. I'd actually like, can I get like a little different definition over here that I like a little bit better, but it's a little bit longer? Okay, thank you. So I'm gonna say amplitude is the vertical distance from midpoint to high point. The vertical distance from midpoint to high point. I like that definition a little bit better. So we're saying for our parent function here, sine x and cosine x, that is 1. So if we look back at our cosine graph, which we can still see here on the screen, you can see the midpoints are right here. They have a y value of 0. The high points have a y value of 1. So that distance is 1, correct? So that's why the amplitude is 1. Same thing for our sine graph. If we grab any one of these midpoints, the distance from a midpoint to a high point, the vertical distance is 1. All right, the period, the length of one cycle we talked about is 2 pi. That is going to change, not today, but when we do some more of these notes next week, it's possible that that can change. But for these ones, for the parent functions, it's always 2 pi. The domain is always going to be all real numbers here on all sine and cosine graphs. We kind of saw that domain going left and right forever when we looked at Desmos, right? And we're scrolling left and right, it goes forever. If we want to do interval notation for that, which I know we haven't done interval notation for a while, so let's get a little refresher there. That would be negative infinity to infinity for the domain. Remember interval notation? Yeah, all right. The range on these ones is going to be -1 to 1. So let's write that in interval notation as well, which would be negative or bracket -1, comma 1 bracket. Now that can change on the transformations, but for the parent functions, it's always going to be -1 to 1. And then one more note here, which we already talked about, the cosine curve is really the exact same as the sine curve, shifted pi over 2 radians to the left, okay? Awesome. All right, let's go on to the next page. It says here we can have a more accurate graph if we add in the other values. I don't like to do that because they're tough to graph. So let's just skip that.
Takes a while too.
Yeah, it does take. I agree with that. Let's go down here though and talk about transformations. Now I've kind of done the same copy paste mistake here again. So can we switch one of these to cosine? Oh, I should have just switched the top one to cosine. That would have been easier. Whatever, doesn't matter. The point I'm trying to get across to you here is that when we have transformations, which is what we're going to mainly talk about for the rest of the day today, they affect sine and cosine graphs in the same way because these graphs are so similar, okay? So we have these kind of numbers that may or may not be in these different spots. So I'm going to go ahead and I'm going to do some highlighting here. So you can highlight with me if you have a highlighter, or you can just circle them. So the absolute value of A is going to determine the amplitude, okay? So A may be positive or negative, but the amplitude will always be positive. It actually makes sense because it's technically a distance, right? We talked about. Now, if A is negative, the amplitude is still positive, but the graph has a reflection across the x-axis. So we're going to be seeing some of that today. All right. If you have a number adding outside of the sine function, that's going to be a vertical shift. And if you have a number adding or subtracting inside the sine or cosine function, that's going to be a horizontal shift, okay?
Which, as we heard a long time ago, the B lies.
That is correct. And I was just about to talk about that. So thank you, Nicholas, for reminding me. So yeah, I was going to say for the vertical shift, if it's adding that number, that's going to move it up. And if it's subtracting that number, that's going to move it down. And once again, that's going to be adding or subtracting outside of the sine or cosine. And if it's adding or subtracting inside of the sine or cosine, it's kind of counterintuitive here. If it's subtracting, it's going to move it to the right. You would think that would be left, but it's counterintuitive. If it's adding a number, that's going to move it to the left, okay? So the up and down is kind of intuitive, the way you would think. The left or right is counterintuitive, the way you would not think. Now, although they are counterintuitive, this should actually not be surprising to you because it's a lot like kind of a lot of other functions that you've worked a lot with. So I'm going to say just like, remember you used to do this, like y equals, I don't know, like x plus 3 squared plus 4, like a quadratic in vertex form. So that shifts the parabola left 3 and up 4, correct? Like the outside is up and down, and plus is up, minus is down. The inside is left and right, but plus is left and minus is right. So I know you guys have worked a lot with those parabolas. And so what I'm trying to say is for these shifts, for these up, right, up, down, left, right, it really kind of works the same way for sine and cosine. Those same rules apply here, okay? A lot of teachers help you remember this, but they say like the x lies. And I definitely said that before. So the x lies, but the y tells the truth. I also know that my ex lied all the time. She like nonstop lied, okay? But I'm over it. Like I definitely don't think about it or bring it up in the middle of a math class or anything like that because I've moved on with my life. Okay, good talk. Feel better now. All right, last thing here, and this one, I think if like all these letters are obviously important, A and B and D, but the one, if I was to pick one that's most important, and I'm actually going to highlight in the formula, it's going to be K. Like I think this K value is super important here. And so I'd like to highlight that there. So K is multiplying, kind of like A. A is multiplying in front of the sine or cosine. K is multiplying inside of the sine or cosine. So it's multiplying by X inside the sine or cosine. And what I'd like you to highlight here for K is actually this piece, that the period equals 2 pi over K. So K does not tell you the period, but K allows you to calculate the period, all right? So the period is not K, the period is 2 pi over K. So it's a little different than A, because A is the amplitude, right? Well, absolute value of A, but not a lot of calculating to do. But for period, there is some, all right? All right, cool. So we're going to take a look at some transformations now that the notes have kind of done for us, but we're just going to analyze them. And then we're going to do some transformations on our own, okay? All right, so let's scroll down a little bit here. So we have 2 transformations here to start. We have vertical shifts and we have reflections, okay? So vertical shifts, so this +2 right here is shifted up 2 units, okay? That's an up 2 shift. Now, wait a minute. It's a little confusing here, right? This 2 is in front of the cosine. So isn't that A? No. All right, so let's make a note out here. This is not multiplying.
You could also tell by that plus sign right there.
I agree. So since it's adding and not multiplying, it is not A. All right. For it to be A, it is out front like that, but it's multiplying. It would be like 2 cosine X, not 2 plus cosine X. So what is it then? It's really the up-down shifts, like D, like we saw above. Like we could write just as easily write this as cosine X plus 2, correct? Like the order we add in doesn't matter. I wanted to show you guys that where they put the add addition thing in front because they do that sometimes. So I just want you to know if something is adding or subtracting outside of the cosine or sine, that's your up-down shift, okay? So you can see here what they did. So they have the original cosine graph. So we kind of have to be familiar with how the cosine graph, the original, the parent function looks. And then once you know that, all you have to do is move it 2 units up, and that'll give you the transformed function up 2, okay? So you can see they have like their high point here where they started off was at 1, now it's up to 3. The midpoint was at 0, now it's up to 2. The low point was at -1, now it's up to 1. So that's all they did to move that up, okay? So this one they've done for us. The next one they've done for us as well. We'll get a chance to do some on our own in a minute. One thing I wanted to note here, if A is not 2, what is A? Well, I would say there's an invisible 1 right here. And so the amplitude is still 1. So that's the distance from the midpoint to the high point, correct? So these midpoints are at a y value of 2. The high points are at a y value of 3. So you can see that distance between the midpoints and the high points is still 1. That hasn't changed. All right, let's take a look at the next one here, which says g of x equals negative cosine of x. So this one is the reflection across the x-axis. So when we have a negative in front of this, it flips the graph. So the high point is now a low point. The low point is now a high point. Notice that the midpoints don't get flipped because it's like they're already on the x-axis, so we cannot flip them upside down, right? We still have an amplitude of 1 because you can see here that the distance from any midpoint to a high point is still 1, the vertical distance. And then we'll talk about, remember I told you that cosine usually starts at a high point? Okay, so does this red graph here, does it start at a high point? The answer is no. So this is one where the cosine actually starts at its lowest point. Does it eventually get to a high point? Yes, it does, but it starts at its low point. Why does it start at its low point? Negative out. Yep, negative cosine actually starts at the low point. Okay, so that's the exception to the cosine always starts at a high point. If it's negative, it's going to start at the low point. Got it? Okay. So now that we've done those 2 transformations with cosine, we're actually now going to switch over, and now we're going to do these 2 by ourselves. And we're going to apply the same 2 transformations, but instead of doing it to cosine, we're going to do it to sine. So we need a quick reminder on what the original sine graph looks like. So I will do that over here. So we remember that it starts at a midpoint for sine, goes up and does a hill, goes up and goes down and does a valley, and then finishes at that midpoint where it started. So then what's it going to look like with our up 2 shift? Well, it's going to look the exact same, except instead of starting at 0, it's going to start at 2. It's going to go up to 3, back down to 0, down to 1, and then back to 0. Oh man, that is not a great looking sine graph there. I've probably drawn worse, but I've drawn better as well. Ay, ay, ay. There we go. I'm going to stop there. That's probably the best I can do. So that's it. It affected the graph in the same way, right? It moved it up 2 units, okay? It's just that instead of starting at the high point like we did with cosine, we're starting at that midpoint. So the starting graph is different. Okay, and now we will look at the x-axis reflection. So it's going to flip it upside down. So I'm again starting back at that original sine of x graph. I cannot flip a midpoint because it's already kind of in the middle. So how this changes is instead of going up and then down, I'm going to go down and then up. So when we have a negative sine graph, it still starts at the midpoint. It's just what it does after that that's changing. It goes down at first and then goes back up. All right. Fun stuff. You'll notice I'm only drawing one period of these. Obviously, this goes on forever, but I can't just draw a graph forever for the rest of my life, right? So we usually draw 1 or 2 periods based on the instruction. Honestly, when we're doing these on WebAssign, it's mostly going to be multiple choice. So you'll have the equation and you'll have to pick the correct graph. So if you're familiar with these transformations, you're just going to be able to look and see them. The other thing we're going to do, which we're going to practice more next week, is they'll show you a graph and you have to type in the function. So you have to be like, you have to look and see, okay, here's what the amplitude is. There's an upshift. I have to type that in. So that's how they'll do the free response ones, I think. All right, let's talk about amplitude for a few minutes and then we'll wrap up here for today. So we talked about the A value out front, the multiplier in front of the sine or cosine is the amplitude, although it must be positive. So they have put here again, they've put the sine graph here in blue. So take a look at that y equals sine of x in blue. That's the one we've all been working on all day. So you start at the midpoint, go up to 1, back down to 0, down to -1, back up to 1. Next one I'm gonna look at is y equals 3 sine of x. So they've changed the amplitude to 3 by multiplying by 3. So it starts at the same point, except now it goes up to 3 and then down to -3, okay? So that's that distance between the midpoints and the high points. It's not a shift because the midpoints are at the same spot. It's a stretch, really, if you think about it, a vertical stretch. So it goes starting at 0 up to a y value of 3. That's that vertical distance of 3. Then the black graph here, you can see is y equals 1/2 sine of x. So that one, instead of going up to, it still starts at the midpoint, but instead of going up to 1, it only goes up to 1/2 and then only goes down to -1/2. So it goes just as far down as it goes up, correct? Except it's in the negative direction. Then the last one here is -2 sine of x, correct? Now, remember, on -2 sine of x, we still say the amplitude is 2 because amplitude must be positive, correct? So the distance from a midpoint to a high point is still 2. But its negative is shown by the fact that although it still starts at that midpoint, it starts off by going down and then up, as opposed to the rest of these, which went up and then down. So that was our only negative one. But so yeah, remember when you have a negative number out front, it's kind of 2 transformations. So the number is the amplitude and then the negative is the reflection. That's probably the best way to think about when you have a negative number multiplying out front. It's really 2 transformations. Let's go ahead and graph the y equals +2 sine of x just below this, and then we'll be done for the day. So kind of referencing that blue y equals sine of x graph again, that's in the picture. So 2 sine of x, we'll still start at that midpoint. And then we're gonna go up first to the y value of 2, and then back down to the y value of -2, and then back to 0 where we started, okay? So that's amplitude, stretches it out. But those midpoints, like I call them, do not move based on amplitude, right? Those are still at the 0. It's just how high the high points go and how low the low points go, all right? All right, cool. Do we have a meme for this? Yes. Let's look at a meme. How about that? That's a good way to finish the day. There we go, gang signs, all right? So apparently this graffitier, at least he knows that the sine graph starts at a midpoint and goes up and then down from there. So good knowledge of his trigonometric graphs on his graffiti. Awesome.